Good morning and welcome to number 4. This should be a good one. It occurred to me that I hadn't introduced one of the most valuable tools in dynamic reverse engineering because I assume that is already in your toolkit, but it's almost certainly not the case. Let's go through concolic execution with GDB. Yes, concolic execution is generally associated with the project that introduced the term Anger, A-N-G-R. Concolic is a word that describes concrete symbolic execution of a piece of software. So you use symbols to understand what's going on until you end up with an instruction that you don't, at which point you use an emulator or execution to determine the result. And so we'll go through that. So let's start off with introducing 000-200.bin, and like the previous one, 100.bin takes in an input, and unlike 100, there's no password in there. You can see hi there, PTE1, believe me, there's nothing for you there. So the question becomes, how does this program work? Well, we'll just start off with, info files. You can see it's got these numbers, so these are the wrong addresses. But if we look entry point 10C0, and then we have 1080, right? So if we go to 10C0, you can disassemble. Let's just do like 100 bytes, right? So, or 100 hex. Uh, 100 decimal in hex is 64. We could have just added 64 if we wanted to, but yeah, it doesn't matter. So you can see NBR64, XOR, blah, 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 call. This is not our main. So, in order to get to the function where we want to attack, we need to find main, right? It's kind of interesting there. $1080. Wonder what's at 1080. This is our main function. So yeah, you can see load effective address, call puts. So yeah, this is definitely our main function. So that was how easy it was to find main. So you can break here if we want. Or you can do something else. You can see this call function to 1200. That's our thing. So if we break there, it won't work, right? Remember how GDB works until you start the program. So we could do start I, or we could break at here. Let's do start I. So now we have all the correct addresses in info files. So you can see it updated them all. We could have just done the math, but I find it easier to double click. It's kind of how I work. Double click there, Q, and break, and it's 1200. So we go 200 there, right? We don't put a 6 here because of how this works. Because the starting address is like the map is 55554, not 55555. Kind of see that with the 1080, right? Yeah, 1080 there, 1200 there. So you take the 1080 and you convert to there. Anyways, you get the idea. Continue, and then if we do x/s RDI, right? We get the input variable. So now we can start reverse engineering this. Makes a little bit of sense to, oh weird. Where did my window go? Did I just close it? Okay, no big deal. Let's back up. It's gonna take a minute, don't worry. So, there we go. Oh, weird. Wait, where'd that, oh. That's funny. Okay, so we'll just increase the font size here, and what I did here to create this is to emit the assembly from GCC, so we're missing a whole lot that you would find in the object dump or the disassemble, but there's no reason to go through those. Those are just, you know, junk that you need for exploitation and you know, stepping through something. I can show it to you, but first, let's go step by step. NBR64, I don't know what it does. I don't think it does anything of value. So here we can put a comment. Spoiler, it does nothing. Secondly, this one takes the first byte of hi there and puts it into EAX. So EAX is equal to H, right? Which is 0668. So it's 68 hex. And then remember how test jump is equivalent to an if statement. So this is if if EAX equals 0, return, and this value here is the value -16, right? That's what happens there. And of course, there are no negative numbers in machine code, just interpretations. And then here we have EDX equals 0, right? It's XOR of an object with itself is setting that to 0, so it's just a handy way of doing that. SI equals -16. Let's figure out what -16 is, though. We can use GDB to find that. Just switch over. So yeah, if we do x/10i RIP, we get 10 instructions from current pointer. So you can see NBR moves test jump XOR move. So this is -16 here. You can see that -16 is represented as a very large number in unsigned. Yeah, that is a way to represent that in a way that makes more sense to us. You'll see why later. then the next one is kind of cool because if you think about it, it's like loading this address into here. So it's adding RIP to val, putting it into there. This is a array thing. So R8 equals val. Got our comment there. And so then we're only going to go to mul here. So here move is RCX equals RDX. Remember, we're in AT&T syntax where the destination is the second one. Intel syntax, it's reversed. It's not a big deal. You see, and is logical and, so they take ECX and equals 7. And of course, remember how RCX and ECX are related. RCX is a 64-bit version of the register, which is ECX. So we need this ECX equals RCX and 4, 1, 2, 3, 4. So that's 8 Fs, right? To turn it into a 32-bit variable. And then we know that the destination here is EAX, and we know the operation is multiplication. But until we internalize what imul does, we don't really know if it's like R8 times RCX times 4, or if it's R8 plus RCX times 4, or if it's R8 plus RCX plus 4. I actually know the answer, but yeah, let's just put some question marks here. And then let's go, right? I think that's worthwhile. And then we'll get the payoff, which is the whole function. So if we do step I, you can see that we got some nops down here. I'm not sure where they came from, but we'll just step through them. And that x/10i helps us find where our imul is. So we want to break there. And then step I, breakpoint 2. So let's print out the inputs, and then we'll step and print out the outputs. R8. Cool. So that's that is in our data section or RO data section. Doesn't matter which. It's something like that. And remember, we put RDX into RCX, and remember how we XORed RDX. So RDX is going to be 0, so RCX is going to be 0, and then this AND just, reduces that further. So it's going to be 0. But let's do that. Yep, it is indeed 0. EAX tells us what we're adding to, and that is the H, right, in high there. So we're going to dereference this, and so we can just take this and do x/wx to find out what value is in there. So we get 27. So we should expect 68 times 27 to appear in EAX. So let's do our prediction. And that's the decimal representation. We want the hex FD8. So yeah, that's what I saw before. FD8, like file disk 8. And there it is. So what we found was for this loop, see here. Yeah. EX multiply by R8 when RCX equals 0, right? And then in the next loop, we find EX is equal to R8 plus RCX times 4 when RCX is equal to 1, dot, dot, dot. So there is our reverse engineering of this one instruction. You could, of course, if you know what that instruction does already, you can just reverse engineer it. You can just like reverse engineer it without GDB, but in this case, do that. So now that we've done concolic execution, let's open up what the heck happened? Oh, like what the hell? Yeah, my brain isn't working, it's too early. There we go. So this is the one where I went through each one and did the math. We can fill this one in. So R8 of RCX, right? And then step by step, and we have this one, same idea, R8 of RCX. And then here's an interesting one. It just dereferences dereferences the high there again. So it's our input value. There you go. And remember how, you have this ECX and RCX thing. So when you do an operation on ECX, you have to do that operation on RCX, or else things go wrong. And then we copy that file into a new file, right? And then we convert it to Python. So is this the right one? I think this is the right one. No, this can't be the right one. Maybe it is. Maybe it is. So yeah, you can see here that I've converted the first part to Python. And then we have just step by step converted to Python. See why this is interesting. And then you have your, this is just a Pythonization of, checking if it's 0 and breaking. And yeah, you can see all very logical instructions. And so let's test it. We first should go into GDB and find out what the return value is. So we need to go to the ret. So let's find where the ret is. Let's just do x/10i. Oh right, we aren't, yeah, we need like 20i to find the ret. So is this the ret? I think that's the ret there. So if we break there, oh, that's not the ret. Wow, that was a close call. Here's the ret. So I remember it from the previous one. So you can see jump, move, ret, right? So there's our end. So then we do continue, see it gets to breakpoint 2 a couple more times, and then breakpoint 3, and then step IREAX, right? So we get a 24666 from this. Continue, it exits, and then F0. There's our 24666. And in previous attempts at this, I had it running on iter tools to find a value that that solves it, and it can't because this is a very, very difficult problem. But we can go to the command line, import this 00200 dot obscure of hi there, right? We get our 24666, right? And then if we put in another value, like we get a larger value, and then a larger value still. So let's just multiply it by 10. You can see the value gets larger and larger. But is it getting larger? Yeah, it's still getting larger. You can see now it's a 32-bit value. It's not going to get too much larger, is it? Yeah, see there it got smaller because we're dealing with 32-bit integers. I assume that that's true. Yeah, we've got this, if you look at the Python code, we're taking this and FF. So we're actually wrapping around, which means we're at the point where we can actually solve this. So now that we have this, sorry, if we get rid of Kate. Now that we have this that wraps around, we can start modifying it in order to get a different number that that gets a 0 value, right? So that's our that is our goal, is to get a 0 value in order to get the win condition. So the question is, how big is this now? Okay, it's only 1.3 megabytes. So that's totally sensible. No, I don't think you can fit that on a command line. I wonder if that will actually, you could run subprocess, and would that actually work? I don't actually know. I'm curious to find out though. But this is already getting too long, and I don't think we're going to find a solution, which means next time we will attempt to actually solve this. We have done concolic execution, and if you want to go deeper, there is a deep rabbit hole. Go ahead and check out anger. Here's how to spell it. And good luck at all your projects, GDP or otherwise.